Hello and welcome everybody. Today in calculus we will be talking about work. This is part 2 of the section 6.4. So there are a total of 3 parts, and I figure breaking it into 3 parts might be a little bit easier to swallow. So let's go ahead and get to it then. Okay, so today the work that we're going to be talking about is hoisting something up from the bottom to the top. So for example, in this case, we'll be pulling a rope from the top of a building. So here we go. Let's go ahead and begin then. So in this scenario, we're going to have a leaky 5-pound bucket, which is going to be hoisted from the ground to the top of the building that is going to be 20 feet tall via a rope of the same length. So you can see that in the picture on the right-hand side. The rope itself weighs 0.08 pounds per foot. Then the bucket starts with 2 gallons of water, which is equivalent to 16 pounds, and it leaks at a constant rate. It finished draining just as it reaches to the top. The rope is hoisted at a constant rate as well. What is the total work done in this case? All right, so as we said in the previous section, when it comes to work, it is going to deal with 2 things. We're going to look at a force, meaning that's something that has a weight, and then the distance, meaning how much you're going to push or pull it. So in this case, we're trying to pull something up, which is going to be the rope, the bucket, and the water, and we're trying to hoist it up to the top. So there's going to be a distance that's going to be traveled. But unfortunately, because the weight of each one of these items is changing consistently, then that means that it's no longer as simple as just work is equal to force times distance. This is where the calculus portion comes in. So let's go ahead and try to figure out what's the total work done in this scenario then. So first, what I'm going to do is I'm going to go ahead and break it into 3 parts because I feel like, taking it by their 3 components might be a little bit easier to digest, just like the whole work scenario. Okay, so the first thing we're going to look at is the bucket itself. Okay, so let me go ahead and change the pen just so that you can see a little bit better. Here we go. Okay, so let's go ahead and change it. All right, so first we're going to look at the bucket. Now, the bucket, again, it's just, again, looking at work is equal to force times distance. The bucket is the simplest case out of the 3 because the weight of the bucket does not change, right? It's always going to be 5 pounds, no matter at what point you are at the hoist, right? If you disregard the rope and if you disregard water, the bucket itself is always just going to be the same thing. So what that means is if I want to find a work for pulling up just the bucket, that is just going to be a force, which is a constant, times a distance, which is a constant. The force in this case is supposed to be 5 pounds. That's how much the bucket is weighing. And then the distance that you're traveling is going to be 20 feet because you are going to pull it up to the top. So then the grand total in this case is going to be 100 foot-pound then. So that is going to be the work for the bucket. So that's the easy part. Now let's go ahead and look at the next part right here. Let's go ahead and consider the rope. Now, for the rope, if depending on where you are, right? Depending on where you are, you're going to have more rope or less rope. Because if you're if the rope is like nearly completed, pulled it to the top, you're going to have less rope to pull. But whereas if you're at the bottom, then that means that you have more rope to pull. So here's what I'm going to do. I'm going to go ahead and first of all label the following: the height, which is going to be given as 20 feet. Next, I'm going to go ahead and give it a variable. The variable that I'm looking at is the distance from the very bottom to the top. It could be somewhere else. If you want, you can make it from the top to the to where the bucket is. But in this case, I'm just going to go ahead and make it from the bottom to where the bucket is. So what we're doing is we're looking at an instantaneous moment to figure out what is the force of that rope then. Okay, now first, I think what we need to do is we need to look at the length of the rope, okay, because that is going to help us figure out what is the what is the weight of the rope. So the length of the rope, right, at any instantaneous moment x is going to be equal to 20 minus x, because you can kind of see it over here in the picture that this length right here, that is going to be distance, and because the whole thing is 20, x is the distance from the bottom to the bucket, then that means the length of the rope is going to be 20 minus x. All right, so now going back to this part, in addition, let me go ahead and write the unit for this. This is going to be in terms of feet because that is the unit of distance that we're using. Okay, so that's the first part. Now, if I know the length of the rope, we can then use the density that's given to us to figure out how much does it actually weigh. Okay, so the weight of the rope, right? The weight of the rope what we're going to do is we're going to take the length of the rope, which is the 20 minus x, that's in terms of feet, and multiply by the density that was given to us, which is 0.08, and then that's going to be pounds per foot. So you take a look at the units, they cancel each other out. So as a result, what we have now is going to be 0.08 multiplied by 20 minus x, and that is going to be strictly in terms of pound. So right there, that is going to be the force, right, as an equation, which is equation that is directly related to the length of the rope. Okay, now that we have the weight of the rope, I need to look at how much distance that weight has to travel. So the distance that it has to travel is going to be equal to delta x. The reason why it's delta x is, remember, the weight of the rope is changing constantly, right? So that means that all we can do is pull it up just a little bit before the weight changes. And then that means that we're going to have to use a different setup each time. So at best, what we can do is just pull it up a little bit. Okay, so that's going to be our distance. That's going to be our distance. And then afterwards, we're going to have a new weight, and then we have a next delta x, and then a new weight, and next delta x, and so on and so on and so on. So putting it all together, the force, right, which is going to be equal to work. Oh, sorry, not the force. My fault. The work. That's what we're trying to solve for. Okay, the work at any instantaneous moment is supposed to be equal to force times distance. So with what we have, that's going to be 0.08 multiplied by 20 minus x, and then multiply by the delta x. And the delta x, the unit over there, that is going to be in terms of feet. So notice that you have pounds, you have feet right there. So there's that foot pound that you want, which is going to be what work is going to be for the unit. That is going to be the instantaneous amount of work at any time. If I want the total work, then that's where you're going to sum every one of those instantaneous moments. So that's where we're going to throw the summation in front. And as soon as you see, again, the summation and also delta x, then that means that that's where we're going to treat it as an integral then. So this now translates to be the integral of 0.08 multiplied by 20 minus x dx. And your boundary, well, looking at my boundary, we're going to hoist it from the very bottom over here to the very top over here. So that means my boundary is going to be from 0 to 20. So if we can solve for this integral numerically, then that means that we have the total work done for the rope then. So this shouldn't be too bad. Let's see if we can do it right now. We have 0.08 multiplied by 20x minus 1/2 x squared, and then boundary from 0 to 20. So let's see, that's 0.08 multiplied by 400 minus 20 gets squared, so that's 400 minus divide by 2, so that's equal to 200. So then it's going to be 0.08 divided by, 8 divided by 100 multiplied by 200. So the answer looks like it's going to be 16 then, and that is going to be in terms of foot pound. Okay, so all of these guys that we're solving for right there, we're going to save each one of them because the sum of all of them is going to give us the total work then. Well, we have the bucket, we have the rope, and then now the last thing is we're going to go ahead and look at the water. Okay, so the case of the water, well, it's going to be very similar to the rope. What's happening is that for the water, you are going to start with 2 gallons of water, which is equal to 16 pounds. And then by the time you get to the top, you're going to have no water left. So what that means is you're going to have a force equation for the water that is similar to the rope. Now, in order to get this equation, I think the easiest way is to think of it as, number 1, a linear equation because you're hoisting it up at a constant rate. And also number 2, well, you're given 2 coordinates to work with. When x, which is the height, is equal to 0, your weight in this case is going to be equal to 16, was it 16? Yes, 16 pounds. Okay, so 16 pounds. Oops, sorry, wrong one. Let me go and change that. Okay, so 16 pounds. Then when you get to the top, which is x is equal to 20, the weight in this case is going to be equal to 0 pounds. So what that means is you're really given 2 coordinates over here, like we said, 0, 16, and also 20, 0. And if you can find that linear equation, then that is going to be your force equation with respect to the distance. So we'll go back to algebra 1 and do this right now. So the slope is equal to 0 minus 16 divided by 20 minus 0. So that's negative 4/5. Y is equal to mx plus b. So that means y is equal to negative 4/5 x. And then that is going to be plus 16 over here because this is my y-intercept. And so this is going to be my force of the water then. Okay, so that's going to be the force of the water. Now, the distance that it has to travel, it's going to be the same thing as the rope, which is going to be delta x because you're only increasing it by a small little increment before your force changes once again. So put it together. So that means the work for the water is going to be those two multiplied together. So negative 4/5 x multiply, 4/5 x plus 16 multiplied by delta x. That's going to be the work of the water at any instantaneous moment. And I'm just going to go ahead and put down the word instant just to make sure that you know where that's coming from. And the one what we need to solve for is the total work. So that is where we're going to put the summation in there because we want to sum up every one of those instantaneous moments then. So negative 4/5 x plus 16 multiplied by delta x. So put it all together, then that is where, again, our integral is going to come from. So 0 to 20, because again, you're hoisting it from the bottom to the top of negative 4/5 x and then plus 16. And then we have dx. And if we solve for this integral, then that should give us what we need, okay? So just to kind of save you a little bit of time, I did it ahead of time. So this is going to be equal to 160, and that's going to be in terms of foot-pound also, okay? So take all of our answers, and then that should be it. So we have 160, we have 16, and then we have the 100 from the very, very beginning. So that grand total is going to be 276 foot-pounds. So that's going to be the total amount of work done by for lifting everything. All right, so if we break it again into components, I think that'll make things a lot easier. Now, some people also are thinking, okay, well, is it possible to combine maybe the bucket and also the water all at once? Because technically, if you put it together, it should be the same thing. And the answer is yes. So in that scenario, maybe what we can do is we can say that at x is equal to 0, the height at the bottom, you're going to have the weight is going to be equal to 5 pounds. 5 pounds. I can't write it for some reason. So 5 pounds. Okay. Whereas the height when x is equal to 20, your weight is going to be equal to, oh wait, it's not 5 pounds, it is 21 pounds because you have the bucket and also the water. So it's 16 plus 5. Okay, so that's where 21 comes from. Whereas when you get to the very top, your weight is supposed to be just the bucket, which is 5. So if you use that as your linear equation, then that will combine the bucket and the water together at once too. Okay. All right, so now let's go ahead and move on to the next one, which is going to be kind of a similar idea, if not almost the same. But this time around, we're going to move out of the United States and go to some other parts of the country where they are using kilograms and meters and so forth. It's just us in the US for some reason that likes to be special. Well, anyhow, so here is scenario number 2. We have a rope that is supposed to be 80 meters, and it's being pulled up from the top of a building just like before. This case, the density of the rope is supposed to be 0.25 kilograms per meter. Attached to the rope is a 1 kilogram bucket. So you can see that in the picture on the right. At the very bottom, the bucket itself is empty. And what's going to happen is now it's going to start to rain as you pull it up. So you can see again that it's raining. So because of the rain, then that means that the water is going to be accumulated in the bucket. So as it says right here, it begins to rain and thus collecting water at the rate of 0.01 kilograms per minute. So this is where it's a little strange because you'll notice the units, it's kilograms per minute. So there's a little bit of time involved. The rope, it moves at a rate of 10 meters per minute. And then assuming that the rope does not absorb any of the water, because that would then make it into a Calc 3 problem because you have double integration, find out what is the total work done. Okay, find out what is the total work done. All right, so let's go ahead and go at it the same way, but this time we're just going to go ahead and, look at mass and acceleration and all that stuff implemented into this. Again, we'll go ahead and take it one step at a time, okay? So first, what I'm going to do is we're going to go ahead and look at the bucket. So for this bucket over here, you just like the previous problem, if you're just looking at the bucket by itself without the rope and without the rain, then that means it's just going to be consistent. So the work is going to be equal to 1 kilogram multiplied by 9.8 meters per second squared, because that right there is supposed to be your force, since it's supposed to be in terms of Newton, multiplied by the distance that you have to travel. Now, the distance in this case is supposed to be 80, because that is going to be the total length then. Well, actually, I didn't technically clarify that, because here's what's actually happening, and I and I said it wrong. The length of the rope is supposed to be 80, so that means that from the top all the way to some point, some arbitrary point, that is going to be the 80. Okay, we don't actually know how high the building is, but in this case we don't really care, because all we care about is that we're still pulling the bucket up 80 meters then. So the total distance traveled is going to be 80 meters over here. So take all of those guys, multiply it out, and then that should give you the bucket. Okay, let's see, did I solve for that ahead of time? Well, probably not, but we'll go ahead and deal with that in just a little bit. Okay, so now let's go ahead and look at the rope. Okay, let's go ahead and look at the rope. Now, for the rope, I know it says that we're going to go ahead and pull it up at a rate of 0.01 kilograms per minute. But that is actually irrelevant in this case, because all we care about, again, is the length of the rope and how much of it do we have, so then that way we can determine what is the weight of the rope. Okay, so here, let's go ahead and do it one piece at a time. Just like before, what we'll do is we're going to go ahead and say that the height that you're going to pull it from the bottom of the 80-foot rope to where the bucket is going to be X over here. Okay, not necessarily from the bottom of the building to the top, but it's just going to be from the bottom of the rope to where the bucket is instantaneously at a certain instantaneous moment. So the length at that time is going to be equal to 80 minus X, just like before. And that is going to be in terms of meters. Okay, if you look at the units, that's what we're using in this case. Now, from the length, we can then determine what is the mass of the rope. Okay, so the mass of the rope is then going to be equal to the length, which is the 80 minus X. Okay, and that's in terms of meters. And we're going to take that and multiply by the density of the rope, because that would then give us the kilograms that we want. So in this case, it is, where is it? Where did I put that? Oh, right there. So it's going to be 0.25 multiplied by, 0.25 kilograms per meter. Okay, so you can see the meters canceling out, giving you just kilogram, which is what we're looking for. So this is equal to 0.25 multiplied by 80 minus X, and then that is just going to be strictly kilogram. From there, we can find out what is the force of the rope by taking the mass and then multiplying by the acceleration, which is gravity in this case. So 9.8 multiplied by the previous part, which is 0.25 multiplied by 80 minus X. And that is going to be my force. And it's supposed to be a whole bunch of units. It's like meters per second squared multiplied by kilogram multiplied by, no, that's it. But remember, in short, we just go ahead and call it newtons. Okay. Now, that is going to be my force at any instantaneous time. The distance that we have to travel for that small little piece is going to be equal to delta X, because again, it's going to change after a small little pull. So now if we want to find the work at that instantaneous moment of the rope, that is going to be equal to the two multiplied together. The distance, that is in terms of meters, okay? So these two multiplied together, so that's going to be 9.8 multiplied by 0.25 multiplied by 80 minus X. And then we also have, nope, that's it. That's going to be now newtons meters, or you can say that is equal to joules. Okay. All right. So once we have that equation, we're pretty much good to go, because then now we can say that the total work is going to be the summation of everything that is above it. And that's where the integral once again comes in. So the integral from 0 to 80, let's see, of 9.8 multiplied by 0.25 multiplied by 80 minus x, and then that's going to be multiplied by dx over here. And it looks like for the work part, I forgot to write the dx part in there. So, sorry, delta x part in there, so I apologize for that. So if we can solve for that integral, then we got our answer then, okay? All right, so that is going to be the setup. I guess I can leave the integration to you, hopefully. Now, the last part, we're going to go ahead and look at the rain, right? The rain that is going to be accumulating in this. Now, remember earlier we said that there's a little bit of, switch up in this case because the rate that we're given over here is going to be in terms of 0.1 kilograms per meter and also 10 meters per minute. So that means that there's time involved in all of this. Well, let's go ahead and throw in all three variables at once so you can see what's happening, and then maybe we can kind of come into a better conclusion. So then that way we can eliminate time. So here's what I'm going to do. We're going to go ahead and look at time. That is in terms of meters. Sorry, in terms of minutes, not meters. Then we are also going to look at height, okay? And that is going to be in terms of meters. And then finally, we're going to be looking at the mass at that any instantaneous moment then. And that is going to be in terms of kilogram. So let me go ahead and write all of these on the side. The water is moving at a rate of 0.01 kilograms per minute. So 0.01 kilograms per minute, okay? In addition to that, the rope itself is going to be moving at 10 meters per minute. Okay, so one is going to be the rope and the other one is going to be the rain. And if you're wondering, what does the rain, what does the rope thing have to do with the rain? Well, it's because when you pull the rope up, that's going to determine where you're at specifically. So it is related to the rain in this case. Okay, so anyhow, let's go ahead and put it all together. At t is equal to 0, when time is equal to 0, your height is going to be equal to 0 because remember, you're at the very bottom over here. Okay, so that is when x is equal to 0. At that point, you don't actually have any mass because it's just the rope itself. It's just the rain itself. So that means it's going to be all zeros across. So that's hopefully easy enough. Let's see. Next, we're told the following. Let's go ahead and see if we can implement this part right here. When you are 10 minutes in, according to what we have right here, right? If time is equal to 10, then you have a height which is supposed to be 10 meters. So that's just going by the rate that we're given. And then correspondingly, looking at this second part over here, how much of the bucket is going to be filled? It's going to be 0.01, okay? And that is going to be in terms of kilogram. Let's see, maybe we can go ahead and fill in a little bit more, but I think we should be able to see what's happening at this point. When you get to the very top at the height, which is equal to 80, right? The time going backwards over here is probably going to be equal to, what is it? Oh, actually, wait, hold on. I think I messed up over here. When time is equal to 1, the height is supposed to be 10 meters. So that is my fault. Let me just go ahead and make that modification because it's this rate over here, okay? So what that means is if I'm looking at proportionality, at time is equal to 8 minutes, you should be able to pull everything all the way to the top. And looking at that second part over here, the total amount that's going to be in there in the bucket, the rain, is going to be 0.08 kilograms, okay? So that's the table if we take all three into consideration. I don't really care too much about time, so I want that to be kind of like the middleman that's going to disappear. So I'm going to go ahead and kind of scratch that off. Well, what I really do care about is this table over here, which tells me the relationship of the mass and also the height, which the rain is going to be. What is the mass of the water that's inside the bucket? Well, let's see here. Looking at this, it's still a linear equation, and I think it's a linear equation that hopefully should be easy enough to see. So the mass of the rain, okay, according to this picture, is according to this chart over here, is going to be 0.01 multiplied by the height, which we can call x in this case because that's what we've been using so far. So that's going to be the mass of the rain, and that is going to be in terms of kilogram, right? Because you can see how they correspond to each other, and that's how I came up with the equation. Well, now that we have the mass, we can go ahead and find out what is the force of the rain. Okay, so that is going to be 0.01x multiplied by 9.8 meters per second. So that would then give us newtons. The distance that it has to travel is always going to be delta x in this case, and that's where the meter comes in. And then now we're going to go ahead and multiply those together. So the work at any instantaneous moment is going to be force times distance. So that's equal to 0.01x multiplied by 9.8 multiplied by delta x. And that is going to be in terms of joules because it's going to be the same thing as Newton times meter. And finally, for the total work, then that is going to be the summation of every single one of those instances previously. So what that means as my final setup as an integral is going to be 0.01x multiplied by 9.8 multiplied by delta x, which changed to dx. And the boundary is going to go from 0 to 80 because that is the distance that you have to travel from the bottom of the rope to the very top. So in the end, what's going to happen is you're just going to go ahead and take those and solve for it, and that's going to be your final answer. So you take this guy right here, okay, and then you take this guy right here, and then you also take this guy right here, solve for the antiderivative, use a finite integration, and there you go. That's going to be your answer then. All right, thank you so much for watching. I will see you guys next time. Have a good one. Take care.